Welcome to all of you. 2023 Unit-1 Mathematical Modeling, Semester 6, Mathematics Honors, University of Calcutta. This is the question paper 2023. This is the question in Unit 1. Question 2A1. Show that 1 minus 2xz plus z square whole to the power minus half equal to summation z to the power n Pnx, where Pnx is the legendary polynomial of degree n. Now 1 minus 2xz whole to the power plus z square whole to the power minus half. This is equal to 1 minus z bracket 2x minus z whole to the power minus half. So by binomial expansion, we get this infinite series 1 plus 1 by 2 z bracket 2x minus z plus 1 into 3 by 2 into 4 z square 2x minus z whole square and plus dot 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 so on. Actually, this is the formula. This 1 plus x whole to the power n, this is equal to 1 plus nx plus original formula is this a plus b binomial theorem, a plus b whole to the power n, this a to the power n plus nc1 a to the power n minus 1 b plus nc2 a to the power n minus 2 b square up to plus bn, when n is a natural number, that is positive integer. Actually this a to the power n, a to the power n minus 1 and so on so on. So if we write this 1 plus x to the power n, if n is a positive integer, that is natural number, and x is any real values, and we can get this finite term expansion, this binomial theorem finite term n plus 1 terms, this 1 plus nx plus n into n plus n minus 1 by factorial to x square plus x to the power n. If this n is not a positive integer, not natural number, that is either negative integer or fraction, negative fraction or positive fraction and so on, and modulus of x is less than 1, and then we get this infinite series. This 1 plus nx plus n into n minus 1 by factorial to x square, n into n minus 1, n minus 2 by factorial to x cube plus dot dot up to infinity. So from this n is minus half, so we get this infinite series this, and obviously this term, this 1 minus x, this z 2x minus z is modulus of this less than 1. Now coefficient of z to the power n in this n plus 1th term, this 1 into 3 into 5 2n minus 1 by 2 into 4 into 6 into 2n z to the power n bracket 2x minus z whole to the power n. Actually coefficient of z to the power n, if we expand this 2x minus z whole to the power n, then we get this z to the power n, this z to the power n into 2x to the power n minus n 2x to the power n minus 1 z. So if we multiply by this z to the power n, so we only this, and z 2x to the power n whole to the power n into z to the power n. So and this term is z to the power n plus 1, z term is z to the power n plus 2. So only this 2x to the power n, 2x to the power whole to the power n, 2x whole to the power n, this is the only coefficient this, so we write here this 2x whole to the power n, this. And again coefficient of z to the power n in the nth term, actually this nth term is this nth term. So if we expand z to the power n minus 1 into bracket 2x minus z whole to the power n minus 1, so in this note z to the power n minus 1 2x minus z whole to the power n minus 1, we get 2x whole to the power n minus 1 minus n minus 1 2x whole to the power n minus 2 into z and so on into z to the power n minus 1. We multiply this, so this z to the power 2x whole to the power n minus 1 into z to the power n minus 1, and this term z into z to the power n minus 1, so z to the power n. So we get z to the power n from this and this, multiply this. So the coefficient is this minus n minus 1 into 2x whole to the power n minus 2. So we get this term minus n minus 1 2x whole to the power n minus 2, and this 1 3 5 into bracket 2n minus 3 divided by 2 into 4 into 6 into 2n minus 2. And after simplification, we get minus this minus 1352 n minus 3 actually 2 to the power n minus 1 because this 2 into 1 2 into 2 2 into 3, so 2 common n minus 1, so this is the n minus 1 factorial and 2 to the power n minus 1, and this multiplying 2n minus 1 2n minus 1 by n, and this adjusting this n by 2n minus 1, and this 1 into 3 into 5 2n minus 1 by factorial n, and this n minus 1 factorial into n, and this 2n minus 2 into 2n minus 1, so you get only 2, and this n into n minus 1 and 2n minus 1 x to the power n minus 2, this 3 expression 3, and so on. Using 2 and 3, we see that the coefficient of z to the power n in the expression of 1 minus 2x z plus z square whole to the power minus half, namely 1, is given by this common this 1 3 5 2n minus 1 by n factorial. This is 1 3 5 from 2 and from 3, so we get this x to the power n from 2, and from this 3 is this 3, and so on, for n minus 1th term is this, and so on. And this is the expression for Pnx, the definition of the legendary polynomial of first kind. This is the true for all natural number n. And now we find that P1x, P2x will be the coefficient of z square in the expression of this. That's why we may write this 1 minus 2xz plus z square whole to the power minus half equal to 1 plus z P1x plus z square P2x plus dot 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 dot. So this expression is the coefficient of this is the Pnx. Actually, this is z to the power into Pnx, z to the power into Pnx, and similarly z to the power 1 into P1x, z to the power 2, z to the power 2 into P2x, and so on. This. So finally we get this. This is the generating function for this legendary polynomial. Next question. Question 2a2, prove that Pnx equal to 1 by 2 to the power n factorial dn dxn x square minus 1 whole to the power n, and using it find the value of P2x. And this is the let Vx is the x square minus 1 whole to the power n. Then dv dx equal to this, and v1 is noting this dv dx, and so x square minus 1 whole to the power n minus 1. So if we multiply by x square minus 1 both sides, so we get x square minus 1 into v1. This v1 means dv dx into equal to 2nx x square minus n whole to the power n. And this we get actually this x square minus n whole to 1 whole to the power n is v. So we get this. Differentiating 2 with respect to x, we get this by Leibniz theorem. This x square minus 1 v2. v2 means the d2v dx square plus twice x v1 is equal to twice nx v1 plus twice nv, or x square minus 1 v2 plus 2 into bracket 1 minus n x v1 minus twice nv equal to 0. This expression actually 2 dash. By Leibniz theorem, for successive derivatives from 2 dash, we write this. This actually Leibniz theorem is this u v n, nth derivative is u n v plus nc1 un minus 1 v1, and so on so on. So for this first term is this x square minus 1 into v n plus 2, n plus 2th derivative, nc1 this derivative first derivative twice x v n plus 1, nc2 into 2 vn. So for this term we get this, and for this term 2 into n 1 minus n x v1, so we get this 2 into 1 minus n x vn plus 1, 2 into 1 minus n nc1 vn, and derivative of x is 1, so this, and ultimately last term is this, so we draw here bracket here is minus twice n Vn equal to 0. So after simplification, we get this x square minus 1 Vn plus 2 bracket twice nx plus 2 into 1 minus n into x bracket close Vn plus 1 plus bracket n into n minus 1 bracket plus 2n into bracket 1 minus n minus 2n bracket close Vn equal to 0. So we get x square minus 1 Vn plus 2 plus twice x Vn plus 1 minus n into n plus 1 into Vn. After simplification, we get this. Now Vn plus 2 is the n plus 2 derivative. So we can write this dnv dxn d2 dx square. So this Vn plus 1 dx of dnv dxn. And this Vn is the dnv dxn, dx to dxn derivative. Now we write this dnv dxn equal to y. So this 1 minus z square d2y dx square. Sorry, this is the x square. This is the x square d2y dx square twice minus twice x and dy dx plus n into n plus 1 into y, where y is the dnv dxn, that is dn dxn x square minus 1 whole to the power n. And this equation 3 is the legendary differential equation. And so clearly this y is a solution. This dn dxn x square minus 1 whole to the power n is a solution of 3. Now we know that the legendary polynomial Pnx is also a solution of this differential equation 3. So we can write Pnx equal to some constant a to be determined this dn dx to the power n bracket x square minus 1 whole to the power n. So this x square minus 1 is the x plus 1 into x minus 1. This u, say this u and this v. And by Leibniz theorem, this we write this factorial n x minus 1 whole to the power n nc1 bracket factorial n x plus 1 into n into x minus 1 whole to the power n minus 1 plus dollar plus factorial n x plus 1 whole to the power n. Actually, here we use this dn dxn, this ax plus b whole to the power n equal to a to the power n m factorial ax plus b m minus n divided by m minus n factorial if m greater than 0, m greater than n. And this is equal to 0 if m greater than 0, m is less than n. And this is equal to a to the power n n factorial if m greater than 0, m equal to n. So from this, if we inner derivative of x plus 1 whole to the power n, so inner derivative is this. This a is here 1 and b is also 1. So this 1 to the power n in n factorial. So for inner derivative is for this term x plus 1 inner derivative whole to the power n is n factorial by this formula. And this into v is what x minus 1 n plus nc1, and this n minus 1 derivative. So n minus 1 derivative by this formula is this, and a is 1 is n factorial is the n factorial and n into x minus 1 whole to the power n for this term is the first derivative of this is n into x minus 1 whole to the power minus 1, and this is the n minus 1 derivative is this factorial into this 1 n minus 1 minus n minus n minus 1. And putting x equal to 1, we get pn1 equal to a n factorial 2 to the power n. So a equal to 1 by n factorial 2 to the power n. Hence pnx equal to 1 by n factorial 2 to the power n dn dx to the power n into x square minus 1 whole to the power n is the proofs, is the proof this. And second part, hence find this p2x. So p2x for n equal to 2, put here n equal to 2, then 1 by 2 factorial 2 square d2 dx square x square minus 1 whole square. This first derivative is this 2 into x 2x square minus 1 2x, and second derivative is this 3x square minus 1 this. So 1 by 2 bracket 3x square minus 1 is the value of p2x. Next question, question 2b1. Solve the differential equation d2y dt square minus 3dy dt plus twice y equal to 1 minus e to the power 2t, where y equal to 1, dy dt equal to 0 at the point t equal to 0 using Laplace transformation. Taking Laplace transformation of both sides uh, of the given differential equation, we get L of y double dash t minus 3 L of y dash t plus 2 into L of yt equal to L of 1 minus e to the power twice t. Here, L of yt is the y bar s, say. Now, L of y double dash t is this s square Lyt minus sy0 minus y dash 0 and minus 3 into sly minus y0 plus 2 into ly equal to 1 by s minus 1 by s minus 2. Now using the initial condition y0 equal to 1 and y dash 0 equal to 0, because this dy dt 0 at the point t equal to 0. So we get this L of 1 is the 1 by s and L of e to the power twice t is the 1 by s minus 2. After simplification, we get this y bar. This y bar means this L of yt, this s minus 3 minus 2 by s into s minus 2 into 1 by this. After simplification, we can write this y bar equal to s square minus 4s plus 2 by s into s minus 2 whole square. This taking this as into partial fraction, is a by s plus b by s minus 2 plus c by s minus 2 whole square. These are constants have to be determined, and this, so this comparing this is the identity comparing this numerator a square minus 4s plus 2, and so a plus b equal to 1 minus 4a minus 2b plus c equal to minus 4 and plus 4 equal to 2. So we get this 4 equal to 2, and solving this a equal to half, b equal to half, c equal to minus 1. So y bar equal to a square minus 4s plus 2 divided by s into s minus 2 whole square equal to 1 by twice s plus 1 by 2 into s minus 2 minus 1 by s minus 2 whole square. Taking inverse Laplace transform from both sides, we have y equal to, this y is a function of t, L inverse 1 by twice s plus 1 by 2 L inverse 1 by s minus 2 minus L inverse 1 by s minus 2 whole square. So this 1 by 2, actually this 1 by s, L inverse 1 by s equal to 1. So this 1 by 2, L inverse 1 by s minus a is e to the power at, so half e to the power 2t, and L inverse 1 by s minus a whole to the power n plus 1 equal to t to the power n factorial e to the power at, n equal to 0, 1, 2. So this equal to t into e to the power twice t is the required solution. Next question 2b2. If Pnx is a legendary polynomial of degree n, then so that n Pnx equal to x Pn dash x minus Pn minus 1 dash x, where prime denotes derivative with respect to x. From the generating function of the legendary polynomial 1 minus 2xz plus z square whole to the power minus half equal to summation n equal to 0 to infinity z to the power n Pnx. Differentiating with respect to z, both sides we get this minus half 1 minus 2 xz plus z square whole to the power minus 3 by 2 into bracket minus 2x plus twice z is equal to summation n to z to the power n minus 1 Pnx, or bracket x minus z into bracket 1 minus 2 xz plus z square whole to the power minus 3 by 2 is equal to summation n equal to 0 to infinity n to z to the power n minus 1 Pnx. This is equation 2. Again, differentiating 1 with respect to x, we get minus half bracket 1 minus 2 xz plus z square whole to the power minus 3 by 2 into minus twice z equal to summation n equal to 0 to infinity z to the power n Pn dash x. So we get this z into minus minus cancel 2 to cancel, so z into bracket 1 minus twice x z plus z square whole to the power minus 3 by 2 equal to summation n equal to 0 to infinity z to the power n Pn dash x. Multiplying 3 by x minus z, we get this and this. So this equal to using 2, this 1 minus twice x z plus z square whole to the power minus 3 by 2 equal to this. So this x minus z into this equal to summation n into z to the power n minus 1 Pnx from 2. And this is an identity. So equating the coefficients of z to the power n from both sides, we get this z to the power n. So z into z to the power n minus 1, so we get z to the power n. So coefficient is n into Pnx. And from z to the power n, so x into Pn dash x. And this z to the power n plus 1. And this, so put here n equal to n minus 1. So n minus 1 plus 1, so n. So p n minus 1 dash x. And this is the result. Question C1. So that z minus half x equal to square root of 2 by pi x into cos x, where z and x is Bessel functions of first kind of order n. We know that the Bessel functions of the first kind as g and x equal to summation r equal to 0 to infinity minus 1 to the power r 1 by r factorial gamma n plus r plus 1 into x by 2 whole to the power twice r plus n. Put n equal to minus half in 1. So we get z of minus half x summation r equal to 0 to infinity minus 1 to the power r 1 by r factorial gamma r plus half x by 2 whole to the power twice r minus half. So r equal to 0, so gamma 1 by gamma half x by 2 whole to the power minus half, r equal to 1, this 1 factorial, and this minus 1 to the power r1, this equal to minus 1, and x by 2 whole to the power 2 minus half, that is equal to 2 minus half. And for r equal to 2, we get this term, r equal to 3, this term, plus dot 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 up to infinity. Taking common, x by 2 whole to the power minus half, so we get 1 by gamma half minus x square. This x is x by 2 whole to the power 2 minus half, so x square by 2 square, half into gamma 3 by 2 is the half into gamma half, and this 2 factorial, 3 by 2 into 1 by 2 into gamma half, with gamma n plus 1 equal to n and gamma n. So using this minus x to the power 6 by 3 factorial, 5 by 2, 3 by 2, 1 by 2, gamma half to the power 6, taking this 1 by gamma half common. So we get 1 minus x square by 2 factorial plus x to the power 4 by 4 factorial minus x to the power 6 by 6 factorial. After simplification, we get this. So this is equal to gamma half is this root pi. So whole root over 2 by pi x bracket 1 minus x square factorial 2 plus x to the power 4 by factorial 4 minus x to the power 6 by factorial 6 plus 2 dot. And this is the cos x. So the expansion of cos x is this, hence the result. Here we use this gamma x plus 1 equal to x gamma x for x greater than 0, and gamma half equal to root pi, and this cos x series expansion for real x is this. Next question, C2. Establish that e to the power x by 2 bracket t minus 1 by t is equal to series. Actually, this is the n is minus infinity to infinity, minus infinity to plus infinity, e to the power n j n x, where j n x is the Bessel function of the first kind. Now, the generating function for the Bessel function is j n x. Actually, this is the e to the power x by 2 bracket t minus 1 by t equal to t to the power xt by 2 e to the power minus x by 2t. And this is the actually generating function for the Bessel function of the first kind. Now, e to the power xt by 2, the expanding this e to the power x expansion this. So the expansion this 1 plus x square by factorial 2 x cube by factorial 3 plus factorial infinity for real x. So we can write for this 1 plus x by 2t plus x by 2 whole square t square by factorial 2 plus dot 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 x by 2 whole to the power n t to the power n factorial x by 2 whole to the power n plus 1 t to the power n plus 1 n plus 1 factorial plus dot 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 infinity. And for e to the power minus x by 2t, we get this expression is this 1 minus x by 2 to the power minus 1 plus x by 2 whole square t to the power minus 2 factorial 2 and plus dot 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 this. The coefficient of t to the power n in the product 1 is obtained by multiplying the coefficient of t to the power n, t to the power n plus 1, t to the power n plus 2 in the first bracket with the coefficient of t to the power 0, t to the power minus 1, t to the power minus 2 in the second bracket respectively. So coefficient of t to the power n in the product 1 this, so we get this coefficient of t to the power n is this x by 2 whole to the power n into 1 by n factorial, and this minus x by 2 whole to the power n plus 1 by 1 plus n plus 1 factorial plus x by 2 whole to the power n plus 4 1 by n plus 1 factorial into 2 factorial. So we get this summation into this. Actually this t to the power n into t to the power 0. So here t to the power 0 is 1. So multiplying this, and t to the power n plus 1, and from the first bracket this t to the power n plus 1 is this x by 2 whole to the power n plus 1 1 by n plus 1 factorial is this, and this, and t to the power minus 1 from the second third bracket, and this x minus x by 2. So this is the minus x by 2. So we get this n plus 2, and t to the power n plus 2, and similar way from this x by 2 n plus 2 1 by n plus 4 1 by n plus 1 factorial and 2 factorial here, and t to the power minus 2 from this bracket x by 2 whole square factorial 2 factorial 2, and in this way we get this, and summation is this r equal to 0 to infinity minus 1 to the power r factorial gamma n plus r plus 1 x by 2 whole to the power n plus twice r. This is the Bessel functions g and x first kind. This here we use this n plus r factorial equal to gamma n plus r plus 1 because n plus r being the positive integer. So we can write this n plus r factorial equal to this. Now the coefficient of t to the power minus n in the product 1 is obtained by the multiplying the coefficient of t to the power minus n, t to the power minus n plus 1, t to the power minus n plus 2 of the second bracket with the coefficient of t to the power 0, t to the power 1, t to the power 2 in the first bracket respectively. So we collect this term from the second bracket, that is t to the power minus n from this second bracket, t to the power minus n is this, and next into first bracket in this t to the power 0. So multiply this t to the power minus n into t to the power 0 is 1. So x by 2 to the power n minus 1 to the power n by n factorial. So we get this first term is this x by 2 whole to the power n minus 1 to the power n factorial. And next term t to the power minus n plus 1 in the second bracket. This second bracket is t to the power n plus 1. This is the x by 2 to the power this n plus 1. This is the n plus 1 minus 1 to the power n plus 1 t to the power minus n plus 1. This into from the first bracket is this t to the power 1. So t to the power 1 is this x by 2. So multiplying this with this x by 2 whole to the power n plus 1 n plus 1. So n plus 2 n plus 2. This x by 2. This x by 2. So x by 2 whole to the power n plus 2 minus 1 to the power n plus 1, taking common minus 1 to the power n. So we get minus 1 by n plus factorial n plus 1 factorial and so on. And this is the minus 1 to the power n Jnx as before. So Jnx equal to this minus 1 to the power n to coefficient of t to the power minus n. This coefficient of t to the power minus n is 1. Finally, coefficient of t to the power 0 in the product 1 is obtained by multiplying t to the power 0 into t to the power 0 in the first bracket, in the second bracket t to the power 0, t to the power 1 in the first bracket, t to the power minus 1 in the second bracket, t to the power 2 in the first bracket, t to the power minus 2 in the second bracket. So coefficient of t to the power 0 in 1, we get this equal to 1 minus x by 2 whole square plus x by 2 whole to the power 4 by 1 by 2 factorial whole square and so on. And this is the j0x. So you observe that the coefficient of t to the power 0 and t minus t to the power minus 1, t square plus t to the power minus 2, and t to the power n plus minus 1 whole to the power n t to the power minus n are j0x, j1x, j2x, jnx, and respectively. Thus we get e to the power x by 2 bracket t minus 1 by t is the j0x plus t into e to the power minus 1 into j1x plus bracket t square plus t to the power minus 2 into j2x and plus so on. And this is equal to summation n equal to 0 to infinity t to the power n gnx plus summation n equal to minus 1 to infinity minus 1 to the power n t to the power n gnx. Now minus 1 to the power n gnx is the g of minus nx. So combining this, we can write n equal to minus infinity to infinity t to the power n gnx. Hence the result. Next question, question D1. Find the series solution of the equation 2x squared d2y dx square minus x dy dx plus bracket 1 minus x square into y equal to x square about x equal to 0. Our series solution of this differential equation. And this is obviously this is non-homogeneous differential equation due to the presence of the term x square in the right hand side of the equation 1. Now corresponding homogeneous equation, this equal to 0, right hand side equal to 0. So if we find the general solution of the equation 2, actually this is the complementary function of the equation 1. Clearly x equal to 0 is a regular singular point of this differential equation 2. Let the series solution near x equal to 0 be of the form y equal to summation n equal to 0 to infinity cm x to the power k plus m and c0 not equal to 0. Next, find y dash, y double dash, derivative with respect to x, obviously. Substituting this in equation 2, we get this equation 2 means this 2x square y double dash, the value of y double dash is this, minus x into y dash value of y dash is this, plus bracket 1 minus x square into y is this. So substituting with this equal to 0 or simplifying this x square x to the power k plus m minus 2, so x to the power k plus m, and x to the power k plus m minus 1, so x to the power k plus m, and this 1 into this minus x square k plus m plus 2, and so we get this. And this summation cm common 2 into k plus m into k plus m minus 1, and this k plus m, and this plus 1 is this term, and this minus of this term. So summation cm, this twice k plus m minus 1, this k plus m minus 1 into x to the power k plus m minus summation cm x to the power k plus m plus 2 equal to 0. And this is an identity equating to 0. The coefficient of x to the power k, we get in this equation this c0 bracket 2k minus 1 into k minus 1 equal to 0, and c0 not equal to 0. So obviously this k equal to half and 1 are two unequal values of k, are not differing by integer. Now equating to 0, the coefficient of x to the power k plus m in 4, we get cm bracket 2k plus 2m minus 1 into bracket k plus m minus 1 minus cm minus 2 equal to 0. So cm equal to cm minus 2 divided by bracket 2k plus twice m minus 1 into bracket k plus m minus 1 m greater than equal to 2. And this is the reconciliation, this 5. And equating to 0, the coefficient of x to the power k plus 1 in 4, we get x to the power k plus 1 from 4, we get put here m equal to 1, So this C1 twice k plus 1 into k equal to 0. Is m equal to 1 C1 and twice k plus 1 this k plus 1 to a 2 minus 1 and this k plus 1, so this k equal to 0. Now twice k plus 1 not equal to 0 and k not equal to 0 because this value of k are half and 1, so obviously C1 must be 0. So when C1 equal to 0, then C3 equal to 3 minus 2 1, so obviously C1 0, so C3 C5 C7 are all zeros for odd numbers. Next, putting m equal to 2 4 6 in 5, we get C2 equal to C0 by 2k plus 3 into k plus 1, C4 equal to C2 by 2k plus 5 into k plus 3, and putting the value of C2 from this, we get C0 by k plus 1 into k plus 3, 2k plus 3, 2k plus 5, and so on. And using these values in 3, we get y equal to C0 x to the power k bracket 1 plus x square by k plus 1 bracket 2k plus 3 plus x to the power 4 by k plus 1, k plus 3, 2k plus 3, 2k plus 5 plus dot 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 dot. Next, putting k equal to half and replacing C0 by a in 6, we get this is y equal to a x to the power half bracket 1 plus x square by 2 into 3 plus x to the power 4 by 2 into 3 into 4 into 7 plus dot dot is equal to a into u same. So this x to the power half into this bracket equal to u. Next, putting k equal to 1 and replacing c0 by b in 6, we get y equal to bx in third bracket 1 plus x square by 2 into 5 plus x to the power 4 by 2 into 4 into 5 into 9 and plus dot 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 is equal to b into v same. The solutions u and v are linearly independent solutions. Hence, general solution of 2, that is the complementary function of the given equation 1, is the au plus bv, where a and b are arbitrary constants. Next, to find the particular integral, let the particular integral of the equation 1 is of the form y equal to x to the power k summation m equal to 0 to infinity am x to the power m with a0 not equal to 0. Then find y dash with respect to x, differentiated with respect to x, y double dash, and putting these values in 1, we get this equal to x square. And after simplification, we get this summation am bracket twice k plus twice m bracket k plus m minus 1 x to the power k plus 1 and so on. So this is equal to x square. So summation am bracket twice k plus twice m into k plus m minus 1 minus k plus m minus 1 bracket x to the power k plus m minus summation m equal to 0 to infinity am x to the power k plus m plus 2 equal to x square. This is an identity, this expression, and the term containing the lowest power of x, that is of left hand side of 10, must be x square. This m equal to 0, when m equal to 0, this the x to the power k, and this right hand side is x square. So obviously, this must be left hand side also x square, lowest term. The coefficient of each remaining term of the left hand side 10 must vanish because right hand side only x square term, and these conditions are satisfied by taking k equal to 2. When m equal to 0, this x to the power k plus 0, so x to the power k, so k must be equal to 2. And if we put m equal to 0, so a0 twice k minus 1 and k minus 1, and this is equal to 1. Coefficient this x square is 1, so this is 1. And next term a1 equal to 0. And for this am and also am is equal to am minus 2 by twice k plus twice m minus 1 into k plus 1 is also actually putting the coefficients x to the power k plus m. So this k plus m, we here put m equal to m minus 2, so we get m equal to m minus 2, k m minus 2 minus 2, so k plus m, so a m minus 2. So to get recurrence solution is this, putting the coefficients x to the power k plus m. So so we have this 11 and 12, this condition, and when k equal to 2, then a0 equal to 1 by 1 to 3, k equal to 2, put in k equal to 2. And since a1 equal to 0, So from this reconciliation 12, we must get this A3, A5, A7 are all equal to 0. And A2 equal to A0 by 7 into 3 equal to 1 by this A0 is this. So 7 into 3 into 3 into 1. And A4 equal to A2 by 11 into 5. So 1 by 11 into 5 into 7 into 3 into 3 into 1 and so on. And putting all these values in 9, we get particular integral is this x square by 3 into 1 plus x to the power 4 by 7 into 3 into 3 into 1 plus x to the power 6 by this plus dot. This is equal to fx 13. So the required general solution of the given differential equation 1 is equal to y equal to au plus bv plus fx, where a, b are arbitrary constants and u, v and fx are given by this u is given by 7 and v is given by 8 and fx this particular solution is given by 13. Next question 2d2. State convolution theorem of Laplace transform and using it find L inverse 1 by p into p square plus 4 whole square. This. Now convolution theorem of Laplace transform is if L of ft, Laplace transform of ft equal to capital Fs and L of gt is equal to capital Gs exist respectively for s greater than a1 and s greater than a2, then L of f star gt exists and L of f star gt equal to capital Fs into gs, that is L of integration 0 to t fu gtu t minus u du is equal to f of capital Fs and capital Gs for s greater than maximum m1 a1 comma a2. And convolution theorem for inverse Laplace transform, that is ft equal to L inverse capital Fs and gt equal to L inverse capital Gs, then L inverse capital Fs into Gs capital Gs equal to 0 to t fu gt minus u du is equal to f star g into t. Now L inverse p by p square plus 4 whole square is equal to minus half L inverse ddp of 1 by p square plus 2 square, because ddp of 1 by p square plus 2 square equal to this minus twice p square plus 2 square whole square. So minus of ddp of 1 by p square plus 2 square equal to p by p square plus 2 square whole square. So L inverse of this equal to L inverse of this. So you can write this. Now L inverse of p by p plus p square plus plus whole square equal to this minus half minus 1 t into L inverse 1 by p square plus 2 square. This because L inverse dn dp and fp equal to minus 1 to the power n t to the power n L inverse fp. So is the first order derivative. So this minus 1 to the power 1 to the power 1, and this we get this from this term is this using the formula, and this is equal to 1 by 4t L inverse 1 2 by p square plus 2 square, and this is equal to t by 4 sine 2t, because L inverse L by p square plus a square equal to sine 80, and this is equal to ft, and L inverse 1 by p square equal to t equal to gtc, because L inverse 1 by p to the power n plus 1 equal to p to the power n by n factorial, n equal to 0 1 2 3, here n equal to 1 plus 1. Then by convolution theorem, this L inverse 1 by p into p square plus 4 whole square, actually this 1 by p square into fp is the p by p square plus 4 whole square. So combining this 1 by p into p square plus 4 whole square, this is equal to integration 0 to t fu into gt minus u du. Here fu equal to this u by 4 sine 2u, and gt is the t, so gt minus equal to t minus u into du. So integrating this t by 4 and this integration on u, variable u, so t is independent of integration, so integration t by 4 integration 0 to t u into sine u du minus 1 by 4 integration 0 to t is u square sine twice u du. Sine twice u second function and u is the first function, and by bypass integration from this we get this, and from this bypass integration we get this. After simplification we get this 1 minus t sine twice t minus cos 2t whole divided by 16 is the required answer of this Laplace transform. Thank you for watching this video.